All right, so let's see. I want to know if people would like me to start with a homework, or would like to start with going over the lecture notes, repeating once again what we have gone over, what is especially important, what are the definitions to remember and stuff like that. Any ideas, any opinions on that?
I think you can review the lecture notes first.
Okay. Sure. So, okay. So we are talking about the integer optimization. So by the way, like once you feel like you're lost, you just raise your hand and ask me any question, because it's definitely important that you figure everything out at least now. Okay, so it's the integer programming problems. They are arising from linear programming problems, right? In linear programming problems, we just have a linear objective, linear function as an objective. We have a couple of linear inequalities, several linear inequalities as the constraints, and possibly we have some other like special linear inequalities, such as the non-negativity constraints. And our variables are supposed to be continuous. They are defined over the entire set of real numbers. In this formulation, in the linear programming problems, the coefficients of the constraints Aij and Bi are the parameters of the constraints, and then we have the parameters of the objective, which are denoted with Cj. So they are normally denoted as Cj. Xj are variables, so we are optimizing over the variables x1, x2, x3. So x1, x2, x3 are not like particular numbers. We are trying to figure out what their value is. Going from the linear programming problem to the integer programming problem, or the mixed integer programming problem, we are just changing the fact that part of the variables that we are talking about are integral. They are integer valued, meaning that there is a discrete set over which they're defined, and specifically it's the discrete set of integer nature. Then we are we are distinguishing a feasible set, which is the set of all values of x and y, the variables x and the variable y, that can be plugged into the constraints and satisfy them. We are saying that a point is feasible if it belongs to the feasible set. We are saying that the point is optimal if the value of the objective function at this point, x star y star, is greater than or equal than any other feasible value. So the value of the objective function for any other point from the feasible set. Like we were distinguishing the optimal value of the problem of the problem. It's the value of the optimal solution. It's a real number, obviously. So these are the basic definitions of the problem that we are trying to solve. It's like the mathematical notation of the problem. Any questions on this at this point? Everyone remembers that? Okay. So we are sometimes the problems are infeasible or unbounded, and we have important special cases of the mixed integer programming problem, which are the integer program, when we don't have any continuous variables in the problem. We have binary problem, which is an integer programming problem where all the variables have only two values, 0 or 1, can take only two values, 0 or 1. And linear programming problem is also a special case of a mixed integer programming problem, but with no discrete variables, right? We are also distinguishing a combinatorial optimization problem as a separate kind of type of integer programming problem. In fact, any combinatorial optimization problem can be rewritten as an integer programming problem, but it's much easier. Sometimes it's much easier to think about combinatorial problem as a separate class of problems, just because it's easier to deal with the formulation on this conceptual level. So for combinatorial problem, we are also dealing with like a kind of a function that is defined through a series of numbers, which is basically a linear function. It's a function that for each subset S of a finite set of n elements corresponds a number which is being composed as a summation over all of the indices in the set over which you are optimizing over like that. The summation of over all of the indices that belong to the set, which is our variable at this point, of the coefficients Cj. We also have an optional constraint that a set belongs to some family of sets. So the set that we are like a feasible set for the combinatorial optimization problem is defined by some family of sets that can be represented in some form. We will see later how exactly it can be represented. So we are having a couple of examples. Let me switch to the really important ones. So the first important example is the assignment problem. It's a problem where we are having, like, let's say, n special agents that are available to carry out n missions. Some agents are better for certain missions than other, and there is a cost of Cij of agent I carrying out a mission J. And your goal is to assign the agents to the missions so that the total cost is minimized. We start formulation. We start writing down the formulation with the variables, with defining the variables. In this case, we are defining the variables xi to be the. Okay, let's switch to the correct formulation right away. So this is the better formulation. We define the variables xij to be equal to 1 if agent I is assigned to mission j and 0 otherwise. This does not correspond to any kind of physical constraints. It's just our interpretation. We are defining xij as a variable, a binary variable, and then like the way that we are like constructing this abstraction is in the way that we will interpret the values of xij in the following way: that if it's equal to 1, then agent I is assigned to mission j, and 0 if it's not. Then we need to define the constraints for the agent I. An agent I does only one job, is being represented with the summation over all jobs of xij being equal to 1. And the constraint that job j has only one agent is also represented with a single equality constraint. Sorry, with n equality constraints for each j. The summation over all agents of xij must be equal to 1, just because there's only one agent that is being assigned to a job. And then we have the binary variables xij, and the objective function is the double summation over all I and all j of Cij xij, which is the total cost of us being spending on the entire set of missions. So this is the basic way to formulate the problem. This is how we write it down mathematically. Any questions at this point? Would you like me to switch to some more interesting parts, like something that is definitely not clear? If everything that I'm talking about is obvious to you, probably I would need to switch to some topics that are less obvious to you right now. Okay, so let me clarify with the max min. Okay, there is something in the chat. Okay, very straightforward. That's right. Then there is an important trick of how to put some. So like when you're constructing an optimization problem, sometimes you have to work with the more complex like objectives and constraints, which are not defined as linear functions. And oftentimes it's possible to reformulate or at least approximate um, this non-linear functions with linear functions, and then you can bring some very complicated non-linear problem with non-linear constraints and discrete variables to the form of a integer programming problem. In fact, it's strictly always possible to at least approximate. So you can approximate any problem with any discrete set of variables with some form of an linear integer program. In particular, it's a very important thing to do in case with the max min or min max functions. The conversion into the linear integer programming problem is straightforward and exact. Therefore, I'm putting it here. There's a statement that is like this is a theorem that is saying that if you are given a function g that is increasing in of two variables. One variable is y, it's a scalar variable, and the other variable is x, which is a vector variable. And you're given a problem of maximization of the function g of a minimum over several over several functions. That doesn't matter what exactly these functions are, and x. Then if you have a problem of this form where you have a max min, you can equivalently rewrite it as maximization over of the function g itself, subject to a system of m constraints that is saying that z is less than or equal than fi of x. As you can see, if we used to have a maximum over over minimums, essentially, now we just have the maximum. So we got rid of this minimum at all, completely. In particular, if this function g was linear, we know that linear function is increasing with y, so it could be linear. In the special case, when g is linear, the problem that we will arrive to will be linear problem as well, or linear integer programming problem if our x is a discrete set, right? Is a discrete set of numbers. So we are very interested in the case specifically when g is a linear function. So similarly, this is the conversion of max and min. Very straightforward. Very similarly, you can prove the theorem for the conversion of min max. So min max and max min of linear functions is a very simple object, and you can deal with that without too much trouble just by adding new constraints. Let's take a look at the example. Actually, let me go to the example from the homework. The third homework, everyone has submitted it already, right? It was this Thursday. I'm not mistaken, right? Okay. So let me pull up the question itself. Just one sec. All right. So here we go. There's this Tanis problem that was in the last homework in the homework 3. That is asking you to. Okay, actually, let me go to homework 2. Probably there is a better example. Just one sec. Yep. All right. So there's a problem of ML objective linearization. A classic problem of machine learning is the problem of scalar regression when we are trying to learn the function fx, some function of fa being equal to b from a data set of pairs ai bi. So this is a typical like regression or supervised learning, call it whatever you want. The AI are normally some vectors in RD, the data entry, and BI are the estimated value. Let's say that they are scalar for the simplicity. And f is a parametric function given by some vector of parameters x, and we are trying to estimate this vector of parameters x from this data set IIBI. Any questions regarding? I guess you're all familiar with this problem already. So the classical problem of training the regression is defined as a minimization of a summation of a sum loss function L of bi fx of ai. In our case, we are considering L to be equal to the absolute values of the difference between bi and f. So it can be rewritten as a summation of absolute values. So we are trying to minimize the summation of absolute values of a number, like of a certain number of variable numbers. So we are considering a specific form of the function f of x to be equal to like the transposed a transposed x. It's basically it's just a linear function. It's called a it's just a single layer artificial like perceptron. So we are asked if we can write down the problem of L1 regression, which is this problem, as a linear optimization problem. So like if we are having this this function as an example. The solution for that is the following. We are considering this ML like this is our problem essentially that we are focused on. We are trying to minimize the summation of absolute values of bi minus aix. This is one, like the first step is to just substitute a transposed x into this expression. Then we know that the absolute value is essentially it's a minimum, like it's a we can rewrite it as a maximum between the two numbers, right? We can write it as a maximum between between ai between the value itself and its negative, like its negation. After we have done that, we can apply the theorem. So let me do I actually need to write it down, or is it clear how exactly you write it down as a maximum? Clear. Okay. So after we have done that, we can rewrite that as like couples of inequalities, and we are having 2 times m like two m inequalities in total, and we still have this linear function that depends on zi, like zi, and zi appear in the constraints as like in linear form. So eventually our entire programming problem is a linear programming problem. So this is very simple. Training a linear one layer perceptron with absolute value loss is a linear programming problem. It's very straightforward and very simple. Okay, so now we can discuss the second part of this question, that is asking us to can I just hide it? The second part of this problem is asking us to consider the multi-layer perceptron, in particular the two-layer perceptron, with the rectified linear unit as an activation function. It means that our function fx of a now takes the following form. Now x is being split into several subvectors, w1 through wn, and then v, subvector v. So these are the parameters that we're going to be using instead of x, and the value of f of a is going to be equal to the summation over all j from 1 to l, some value l, vj times the maximum of between 0 and wja. So it's a maximum between 0 and the linear function that depends on wj. Basically, it's a very common problem, especially in the training of computer vision algorithm like deduction. Normally, it's solved in a different way, in a different form, with subgradient algorithm, and but here we would like to know if it's possible to reformulate it as a linear integer programming problem. We can assume here that there is some number m that limits from above the absolute value of any other number in the problem. So we're going to be using this fact. We need to write down the problem of L1 regression in this new case. Let's take a look at how to do this. We can we need to minimize. So essentially we are doing the same thing as we were doing over here. So yeah, so in the second part, we first formulate the objective. It's minimization of summation over absolute values over the residual. The residual is equal to bi minus the function of a, right? The summation over j from 1 to l, vj maximum 0 and wja. So this is our objective function, new objective function. We need to linearize it. To linearize it, we use this the exact same trick that we had here, because our theorem that we have formulated, it doesn't care about the functions fj at all. Like it doesn't really care what exactly you have underneath the maximization over here. It can work with anything. So just by bluntly applying the same theorem, we are getting the following reformulation. Now we have zi greater than or equal than vi minus summation over j from 1 to l, vj maximum over 0 and wja. This even though the objective function is now linear, the constraints are not linear yet. So to linearize it, then we would need to exploit binary variables. Binary variables that are telling us if the value of wja is positive or not. So which value 0 or wja we need to choose for each j. This variable is going to be called tj. It's a binary variable, and instead of maximum of 0 and wja, we're going to be writing the variable as j, which is a continuous number. So like instead of having this maximum, we're going to have a couple. The first value is as j, and then the second value is tj. That will be kind of regulating which value of sj is feasible or not. So we are just substituting, instead of the maximization, we are substituting sj in both inequalities, in the first one and in the second one. Now we need to make sure that sj takes the value of this maximum between 0 and wja. We are saying that sj is less than or equal than the value m times tj, and also sj is like which basically is telling us that sj has to be equal to 0 as soon as tj is equal to 0. If tj is equal to 1, we don't really care about what value of sj there is. Therefore, together with the inequality sj greater than or equal than 0, we are making sure that sj is exactly equal to 0 if tj is equal to 0, right? There's no other way. If tj is equal to 1, then sj can be anything that is above 0. So this can be obtained just by applying this to let me actually draw them. This inequality and this inequality. So far we know that sj is equal to 0 if tj is equal to 0, and sj is anything above 0 if tj is equal to 1. Now we need to make sure that sj is greater than or equal than wja, just because it is a maximum between 0 and wja, so it cannot possibly be less than wja. It always has to be greater than or equal than wja. And lastly, we need to make sure that sj is less than or equal than wja plus m times 1 minus tj. This is telling us that if tj is equal to 1, then sj must be equal to wja, because we know that sj is greater than or equal than wja, and also if tj is equal to 1, then sj is less than or equal than wja. Therefore, if tj is equal to 1, sj is equal to wja. Therefore, we have concluded that if tj is equal to 0, sj is equal to 0, and if tj is equal to 1, then sj must be equal to wja. Now we only need to make sure that tj is equal to 0 and tj is equal to 1 if tj is equal to 0 if and only if wja is less than 0, and tj is equal to 1 if wja is greater than 0. It's fairly straightforward, just because if wja is less than or equal than 0, then we are basically we are forced to have tj being equal to tj being equal to 1, just because of this couple of constraints, right? So we know that sj must be if tj was equal to 0, then we would need to have sorry. So there's a different number. There's a different couple of inequalities. Let me see. So it's the contradicting inequalities are going to be So yeah, so we are assuming that wja is less than or equal than 0, and we are assuming that we will have to have um, sj being equal to 0 if we assume that that tj is equal to 0. So we would have a problem, a contradiction with the essentially the last inequality, and therefore we are not like this is not this is not going to be a feasible solution at all. Any questions regarding the solution over here? Okay, a little confused between TJ and SJ. So basically, the role of TJ is it's a like signaling role. It's an indicator that is telling us if we are in one of the world in one of the cases, if we are in the case that wja is greater than or equal than 0, or wja is less than 0. So we are and sj doesn't like it's the value itself, it's the value of the maximum. So tj is telling us in which case we are, and sj holds the value of of the maximum between the two. Therefore, in the very end, we are only plugging the value of the maximum into the inequalities. So here we only have sj's figurating in the inequalities, and tj only appears in the regulating inequalities that are making sure that sj is in fact the maximum between two. So yeah, you basically you would need to to check that this is the solution. Basically, how I came up with the solution. I had like this couple of inequalities right away. This is not the level of difficulty itself, but you definitely will have a problem of formulation on the midterm and the final exam, where you would need to like come up with an inequality. So this is not the level exactly. I will try to come up with a problem that is simpler than this, but generally speaking, you need to I will try to make sure that you need to utilize both of the techniques, Maximin technique, and also introducing indicator variables to make sure that the variable the values of the variables follow the logical rules. So the problems are going to be around the level of that you are having in the textbook. So this problem is something that I came up with myself just to make sure that people get challenged in the homework. But I believe that the problems in the textbook are much simpler, and I will try to keep everything so that it's closer to the level of the textbook. Regarding the practice problems, I will try to prepare them, but I cannot guarantee that they're going to be released fast enough. So I'm prioritizing the like preparation of the exam problems themselves at this point, and therefore it's it like it's I cannot guarantee you that there will be that like the exact same subset of problems that are going to be on the exam. Absolutely, yes. So if you are making up to this a certain step, if you have some explanations, you will definitely receive the credit. So no worries about the credit. I'm like, yeah. So the main thing is that you understand the problem, you understand the general direction of the solution, and you will definitely receive the credit for that. I understand that this is not a simple problem. But it's a very kind of illustrative example of how elaborate the process of formulation of an integer programming problem can be, generally speaking. I think it's a good example. Yeah. So are there any concerns regarding the problem itself? Like I feel like I could have explained more about why is this the solution for the homework that for the problem that we have in the homework. Is there any interest in understanding more deeply the solution, like the proof that this problem here is in fact the problem that we are looking for? Okay. Sure. Yeah, let's do that. Let me switch to the yeah. So the min-max example is an important one, and then there were other examples regarding the formulation. Let me yeah. So let me give you a couple more of the modeling examples where we are considering basically the logical constraints, the ones that we were formulating just now in this for this homework problem. Suppose that we are planning to go shopping, and we have $1 in cash and $2 on the credit on the debit card. There are two stores in our town. One accepts only cash, and the other one accepts only credit card due to sanitary restrictions. We only have time to visit one of them. How to model the budgetary restrictions of this type? So basically, you are having a set of like your feasible set has the following, but essentially it has this form, where your kind of set of purchases is y1 in case you are like your set of purchases is going to be this triangle here if you go to the first shop, and your set of purchases is gonna be this triangle here if you go to the second shop. And right now you can go to any of them. So your eventual feasible set looks like this. This is not a convex figure even. So it's not even a convex set, and you need to understand how to therefore it cannot be rewritten as an integer programming problem. And what we can do is we can reformulate this problem as an integer programming, as a linear integer programming problem. How to do this is to introduce an auxiliarily variable x1 and possibly also x2 that are telling you to which store you're going, what is the decision that you're making. This x1, x2 are binary variables because they're corresponding to a decision, a logical decision. And now you need to make sure that if x1 is equal to 1, then the first triangle, the first triangle is something that is your budgetary constraint, and the second triangle is not in your budgetary constraint. And if x1 is equal to 0 and x2 is equal to 1, then the second triangle is your budgetary constraint, and the first triangle, it does not affect your budgetary constraint. So when you are putting those together, when you have a choice between picking x1 or x2 being equal to 1, your eventual set, feasible set, is the union of the two triangles, which can be not a convex set. Yeah, so basically this can be implemented with these two inequalities that are saying that a1 y minus b1 is less than or equal than m, like some big number that is bigger than anything in the problem, times 1 minus x1, where basically if x1 is equal to 1, then this constraint is acting, and the right hand side is equal to 0, and we have an actual constraint, a1y less than or equal than b1. And if x1 is equal to 0, then this constraint doesn't mean anything, because we have something on the left hand side that is less than or equal than m, which is a trivial constraint. So we can we just don't care about it. So if x1 is equal to 1, this constraint is going to be acting. If x1 is equal to 0, this constraint is trivial. The same thing is true for the second constraint. Therefore, we have arrived to the, and also we know that only one out of x1 and x2 is equal to 1, because x1 plus x2 is equal to 1, and exactly one out of these two is equal to 1. So we essentially have represented the logical statement of union of two sets. There is a file on B courses and also on the website that elaborates a little bit more on the logical constraints and how to formulate them as integer programming problems. So this is, I would say that this is more like, this is closer a little bit to what you should expect during the exam. This is not a very hard problem in my opinion, and it's doable within a reasonable amount of time. Any questions here? Is this like how do you feel about this problem? Is this a too simple problem, a too difficult one? Here? Yep. Are there any questions regarding this? Okay. Sounds great. Yeah, so then we have been talking about the formulation, and we'll be talking about what is a formulation, strictly speaking. The formulation is a polyhedron that such that the feasible set X can be represented as the intersection of this polyhedron and the set of like and the direct like the product between the integer, like the set of integral vectors times the set of real vectors. It's a formulation for mixed integer programming problems, and for just integer programming problems, a formulation would just not have this real like set of real vectors at all, and we would have only integral vector set of like in like being intersected with a polyhedron. We know that there are multiple types of like for the same problem there are multiple formulation that that are acceptable, and moreover and some of them are better, some of them are worse, and we can compare them. We also have this notion of like we know that there's a notion of an extended formulation that is essentially that it's a talk like it's a formulation like it becomes a formulation after you make a projection. So you can make a formulation in terms of larger number of variables. Normally it actually helps to make problem easier if you make a formulation in terms of a larger number of variables. In this case, you need to like after you have solved the problem in the larger number of variables, and you need to recover the solution to the original problem, you can exploit the projection kind of like algorithm or technique that is essentially just getting rid of all of the auxiliary like additional variables that you have added to the problem when you were reformulating as extended formulation. We might have a problem with extended formulation too. So we have like for the same problem there are multiple equivalent formulations that are possible. We can compare them, and the best formulation that we would pick in this case is a formulation that exactly follows the convex hull of the feasible set. So the feasible like the convex hull is the best formulation possible, and then if one formulation is better than the other if it's inclusion of one set into another. Right. So we have this uncapacitated lot sizing problem that I want to start. I will not stop in details, but it provides with a very good example of an extended formulation and how it can be done, how extended formulation is possible, how to add more variables to make the problem easier potentially. So take a look at this if you would like to understand extended formulations more deeply. Then we had a couple of examples with the like programming and the coding with Python. I will not include this into the exam just because it's I guess very hard to write code on a piece of paper. But generally speaking, we had a couple of like we were discussing the traveling salesman problem within the framework of this algebraic modeling tools, and I would suggest you to go back and revise the formulation of traveling salesman problem as it is a canonical example of an integer programming problem for formulation. So after we have completed formulations, we have switched to the actual solution of the problem, and we have realized that solution of the problem of an integer programming problem is a complicated task, and one thing that might bring us one step closer to its solution is being able to establish bounds on the values of the problem So there are two types of bounds that we can consider. One is the dual bound, which is the upper bound for maximization, and the other is the primal bound, which is the lower bound for maximization. Um, like obviously the optimal value is going to be in between these two, and we have considered multiple algorithms for the or approaches for construction of both of these bounds. The first like set of techniques are called relaxations. Relaxation is a programming problem for which the domain, the feasible set, is larger than the original set, and for the maximization problem, the value of the value of the objective of the relaxation is always greater than or equal than the value of the objective function for the original problem for all of the variables in the original domain. So normally relaxation is an easier problem than the original one, and it allows you to find like a dual bound, this value of the optimal value of a relaxation is always greater than or equal than z if we are talking about a maximization problem. If we are talking minimization problem, it's always less than or equal, so it's dual bound. And there are three possibilities when solving a relaxation. You might have found a solution that does not belong to the original feasible set. Then you essentially, or it could be that if even if it does belong to the original set, its value, its new value might be not equal to its original value. Then we have obtained a dual bound. And it's possible also that after the solution of the relaxation, you actually found something that belongs to the original set, and the value of the objective function for the relaxation coincides with the value of the original objective function. Then you can conclude that you have solved the problem. This is a very important tool to know, and because essentially it works the same way the other way around. So for the primal bounds, it also works the same way, meaning that if you have found a solution that is that belongs to the original set, and its value exactly corresponds to its value of the essentially, if you have found a tight bound, if you have a lower bound and an upper bound on the value of the solution that coincide exactly, then you can prove that you have found the exact solution for the problem, which is a very powerful tool in finding the solution to the integer optimization problems. Then we have talked about linear programming relaxations. It's the relaxation when you just get rid of anything that is integral in the problem. We have considered a couple of examples. We also took a look at the combinatorial relaxation of the traveling salesman problem. It turned out that the combinatorial relaxation of the traveling salesman problem is in fact the assignment problem, and we have found out several ways to write the additional constraints that discriminate between the traveling salesman problem and the assignment problem. So I don't think there will be examples of combinatorial relaxation on the midterm, but there might be some on the final exam. So the next step that we have taken towards the formulation of the dual bounds is so-called parametric relaxation. So it's a problem. It's an optimization problem with a parameter in it. So basically, you can think about it as a set of problems for which like each of the problem is defined by a value of the parameter, and the value of this values of this parameter belong to some set, and so now that you have as like the set of relaxations, each of these relaxations should give you a dual bound, which is the upper bound for your optimization problem if you're talking about maximization. And now you can think about a problem of minimizing this upper bound, bringing it as close as possible to the limit, to the actual solution of the problem, and that is called the duality, the dual problem. The dual problem is the optimization in the space of parametric, parametrically defined optimization problems that result in the best in the best dual bound possible for this problem. We have defined what is a weak dual pair. A weak dual pair is a couple of it's a couple of problems. It's a couple of optimization problems for which the any feasible solution of one is less than or equal that has a value less than or equal than the feasible solution of any feasible solution of another. A strong dual pair is a pair of two optimization problems for which the optimal solutions they are a weak dual pair, and also the optimal solutions to both problems coincide. So the definition of a strong dual pair is valuable, and most probably is gonna be useful for you on your exam. We also have this notion of duality gap, that is the difference between the optimal solutions of the primal of weakly of the primal and dual problem, and it is equal to 0 if we are talking about weak dual pair, a strong dual pair, and it's greater than 0 if it's just a weak dual pair. Any questions regarding what I'm talking about right now? What's the time, by the way? How do you feel about this dual optimization problems and like duality theory in general? Is that something that is obvious to you? Okay, it's clear. Sounds great. Okay, so we have gone over the example of duality, the matching covering problem pair. So you already know how to show that there's an example of showing that a pair of problems is a primal dual pair, and it is possible that there will be a problem like that on the exam. So yeah, I don't think we will discuss in details problem like matching covering. I'm not sure what exactly it's going to be. Matching covering is extremely like common and well-known example. I will try to find out if there is like a suitable like the same kind of level of difficulty problem that is also consists in showing that a pair of problems is like form a primal dual pair. In this case, you would just need to you would need to follow the proof that that is showing that maximum matching and minimal covering form a weak like primal dual pair. You basically need to show that for any feasible point in the first problem and any feasible point in the second problem, the values of the objective form the one objective is less than the other. So it's normally it's just you can just go from definition for this kind of problems, and it's like a relatively straightforward proof. Probably by contradiction, it will be resolved. I'm not so I do not promise you a problem like that, because I still haven't like put together the exam. I actually intentionally haven't put it together, so that I don't accidentally just tell you everything about the exam. But it's most probably is going to be like it is going to contain some kind of problem to show prime, like something about duality that there are definitely going to be. Okay, so yeah, so there are some properties that are interesting. I do not plan to include specifically the questions on the strength of dual problems, but like the topic of Lagrangian duality is important, and like the skill of formulating a Lagrangian dual is something that that you're expected to have. I haven't said that yet, but you are allowed to bring a small piece of like a small cheat sheet on the exam. I believe that cheat sheets are like it's something that help you to condensify information in your head, and if you have a cheat sheet, it actually helps you a lot while you're like it helps you to prepare while you are making the cheat sheet, and it should be very like it should be very like relatively small, so that it only contains the main like the main kind of things that you might forget. So it shouldn't be like a full sized like a letter sized thing. It should be at least like at most half of a letter size cheat sheet. Is that clear? So we can put some definitions that you are forgetting, something like that. Yeah. So it's half of the letter size. I will not be too strict there. So it's like if it's slightly more than half of a letter size sheet of paper, it's probably okay. But it shouldn't be like something that is way larger than half of a letter size. Okay. Any other questions here? Okay, so there will definitely not be anything about additive dual. This is something that is like completely theoretical thing, and I'm not planning to include anything about it. Okay, so let's yeah. So let's switch to the heuristics. The challenge of the primal bounds is that it's like basically the only way to show primal bounds is to provide with a feasible solution. To provide with a feasible solution, so like but basically essentially, if you found a feasible solution, you have found a primal bound. But the better is the feasible solution that you have found, the better the primal bound is. And the question of getting very good primal bounds is an extremely like important thing. And therefore, you are normally not just looking for any feasible solution. You are looking for a very good feasible solution. And for that, we are using heuristics. Heuristic, like the first thing that you can do is to use a restriction. Restriction is essentially the inverse of a relaxation. So essentially, if you have two problems and one is the relaxation of another, then the other is a restriction of the one. So it's like the other way around. So it also includes the inclusion of the domains. It's just the other way around, and it also includes the inequality between the objective functions, just the other way around. And the value, the optimal value of the restriction is always it always provides you with a primal bound for the solution. For the maximization, it's the lower bound. So the first very simple heuristic that you can think about is come up with a relaxation and then solve it, and then like, I know, do a projection onto the space of integral vectors, for example, with the, like, by applying rounding. It's obviously a heuristic, because it's not guaranteed to bring you a feasible solution at all, but it's like oftentimes, first of all, you can make it more complex so that it works in like more often, and also you can like you get like there are in fact a lot of examples of the problem when this particular, even this simple heuristic actually works very well. Another important heuristic that has actually multiple reincarnations, multiple kind of statements of the same idea is the greedy heuristic. The greedy heuristic is essentially telling you that you need to like look at your problem, divide it into parts, into like items, and then assign value to each item, and take those items that are of the greatest value, or like construct an iterative process that selects the items of the greatest value. A very good example of it is with like a greedy heuristic for a knapsack. So for a knapsack, you have a single objective function, a linear objective function, and also a single constraint. And so it's very like it's easy to construct a value function for each item j that is of this form, cj over aj. And after that, we can order them in order of the value being decreased, and then we can go between the items in the order defined by its value, and take items, put the items into the backpack, if we can still fit it into the backpack. And this will not always lead to a feasible, like an optimal solution, but it will normally it will always lead you to a feasible solution. It's not always leading you to an optimal solution. It is very important to know when exactly it's guaranteed to lead you to an optimal solution, and we will talk about it in the next part, in the easy problems part. But generally speaking, it's very important to understand the basic mechanic of the greedy heuristic. Actually, let me so the local search example is so let me go quickly through the examples of the heuristic so that we can go to easy problems, and then I will explain you how to show that the solution provided to you by heuristic is the optimal one. So the local search example is an example when you like of basically restricted search of when essentially you're doing the brute force, you're doing the search over all possible options, or all possible variants. You just restrict the number of variants according to some rule. The rule that in which you're restricting the set of variants you're going over is defined with a neighborhood, the notion of a neighborhood. It can be defined in various ways, but like normally it's just predefined for you in the problem. For example, here you have it's either predefined for you in the description of a problem regarding a heuristic, or you are free to choose one for yourself, depending on where exactly you happen to have this kind of task. The taboo search is like a complicated form of a local search with kind of restrictions on where you can go and where you cannot go from a particular neighborhood. What is the next neighborhood you can switch to after you have completed a sequence of neighborhoods in the past. The simulated annealing has also a very similar framework of jumping between the neighborhoods. It just has some more like probabilistic nature. The genetic algorithm is something that I'm not planning to include because it's just complicated and it's not very like informative, and there are too many moving parts. But all of the previous heuristics could happen to appear in the exam, in the midterm, and then the final. Okay, so the construction of the heuristics normally, like it's so we have gone over the rounding. There's also a very important example of a very simple heuristic that is called fixing. You are setting like some variables to be fixed at some values, and then you treat them as the parameters of the problem, and you solve for the rest of the variables, assuming that this particular variable is like or subset of variables are fixed, and that actually reduces the size of your problem dramatically. So the rounding and the fixing are the two very important examples of heuristics. I just want to stress on this. Okay. There are a couple of examples of heuristics of like more complicated nature. I would say that the feasibility pump is the one that is often applied in practice, and so I will try to formulate something that includes like feasibility pump. But I'm not sure. Like I will not guarantee to you that this is something that is going to be included in the definitely not going to appear in the midterm exam. It could appear in the final exam, but I would give like 20% of that. Right. So let's turn to the cases when actually the heuristics or the relaxations or the dynamic programming problems result in the exact solution to the problem. Can we go over the feasibility pump quickly? Yeah. So essentially, it's a heuristic where you have you are basically using fixing and projection or rounding iteratively. So you iterate projection onto the integral, the set of integral vectors, and the projection onto your formulation P over and over again. It's important because it can be obtained via solution of an LP problem, and that can be done pretty quickly. The projection onto a particular formulation, but normally you also have variation in the formulation itself. So this formulation itself changes between these two iterations. If we decide to so we will most probably talk about it more when we are talking about hard problems further down the line and further in the semester. there could be there might be an example even on the lecture that I'm talking about. But if there is none, I will not put too much attention on it on the exams and the homework. So no worries. Yeah. So basically, we know that after application of relaxations, so after obtaining the dual bounds, or after obtaining the upper bounds, the primal bounds, you might happen to actually solve the problem to the ground, basically to obtain the ground truth of solution of the problem. There's also a method that is neither like a heuristic, or the relaxation, that is called the dynamic programming approach, which is also very important, and we have stressed on that during the past few lectures. It's extremely important to understand how exactly to show that the relaxation is exact, and the greedy heuristic is exact, because it's basically it's telling you how you can put, like, in which form you need to put your problems to make sure that it's easy. It can be easily solved using a very well-known problem, even if it appears as an integer programming problem, which is generally speaking could be very hard. The first big example of of a problem that can be solved over via a simple relaxation is a problem that is based on a totally unimodular matrix, right? So we were talking about an example where we have this matrix A, right here in the formulation P, that defines the formulation P. If this matrix is totally unimodular, then the resulting integer programming problem is simple, and you can just solve it by applying linear programming relaxation. So the property that is telling you what in which case a matrix is a totally unimodular matrix is in fact very important property, because this is something that you can apply even in general case, and see that the problem is simple, and you can just solve it by applying linear programming heuristic. The very important example of a problem with totally unimodular matrix is the minimum cost network flow, and there will be most probably at least one problem that or it's a part of problem that is talking about formulating something as a minimum cost network flow, just because it's extremely important in the applications. Just having this practice, and we have had this practice in the homework too. So please do repeat this material. Right. So there's we have applied the proposition 3.2 regarding the sufficient conditions on total unimodularity to show that minimum cost network flow does in fact have the matrix A totally being totally unimodular, and therefore it can be solved with simple linear programming relaxation. This is one example, but this is one big example of minimal cost network flow that we have considered during the lecture. So please review this one more time. Then there is another example that also utilizes the total unimodularity, but not for the sake of showing that the problem is simple, but rather for showing that a pair of problems form a strong dual pair. So this is another example. Before, in the when we were talking about dual bounds, we have seen an example of a weak dual pair, and max flow mean cut is a strong dual pair, and the way to show it is through total unimodularity. Then we have discussed the shortest path problem. We have seen that this is a problem that is a simple one because it can be formulated as a minimal cost network flow problem, and also it can be solved with a dynamic programming principle that we have discussed in details how it looks like, and also like what is the principle of optimality and how to construct principles of optimality um, for different examples of the problem. For example, the uncapacitated lot sizing problem. We have considered optimal subtree problem, the binary knapsack problem. So these are the examples that are quite important, and I will make sure that there is something about a dynamic programming problem too in the exam. So it's the like basically most probably the question is going to be something about formulate like the principle of optimality for this particular problem, and then you need to come up with a recursive expression of of this form, for example. Right, and then we have quickly discussed submodularity. I have put some effort to explain it during the discussion section. I'm not like I don't think so. This is basically a way to show that a greedy heuristic results in the exact solution for a particular class of problems. I don't think there will be much on submodularity like uh, as like in general, but there could be a problem that is asking you to show submodularity of something, or it could be that using the definition of submodularity show that something is satisfied, because there are actually like more general objects than submodularity, like matroids, like purely theoretical, and there could be some interesting yet simple tasks that you can pull up just by by using the definition of submodularity. And then there's an example of application of a greedy algorithm on a for a problem that possesses submodularity property. Okay, so I think we are like I have commented on all of the topics that we have gone over so far. Are there any questions? Any requests? Like, do you want me to go over something specifically? Like repeat something, stop in more details on some topic? The formulation problem, you mean like formulate a problem like a like a like as an integer programming problem, right? Yeah. So I don't think I have a particular example like that has not been used on like that has not been used so far. But I would say that one option is this minimum cost network flow model. I can just repeat this for you, the entire way of formulation, and the other important option is having a formulation problem with a logical constraint, like the ones that we have gone over during the discussion section. Actually, I can pull up the discussion notes, and we can take a look at what was done there. Would you like me to do that? Okay. Let me see. Okay, so this is actually something that we did not go over. I had to skip it when we were, because we didn't have much time on that discussion section. But the uncapacitated facility location. I think eventually I did I did introduce this formulation during the lecture, but I think it could be useful also to repeat once again. So the formulation looks like this. It doesn't have any any um, it doesn't have any like logical constraints for real. All of the constraints, so it doesn't, you don't have to introduce anything to satisfy any logical constraints. And I will try to include some logical conditions into the formulation problem on the exam. Um, so you basically will have yeah. So we have already discussed a problem with logical conditions. So I'm not going to repeat that once again, but I will give you an example of this uncapacitated facility location problem. So given a set of potential depots n and the set m of clients, suppose that there is a fixed cost fj associated with use of depot j, and the transportation cost cij if all of client i's orders are delivered from depot j. Um, the problem is to decide which depot to open and which depot serves each client so as to minimize the sum of the fixed and transportation costs. Note that this problem is similar to the covering problem except for addition of variable transportation costs. So basically, we are having the variables, the variable xj, that is basically a logical variable here too. But it's more like physical because it's decision on opening a particular depot or shutting it down. So xj is going to be equal to 1 if depot j is used is open, and it's going to be equal to 0 otherwise. Yij is the fraction of the demand of client I that is satisfied from depot j. Obviously, we need the constraints. For example, the constraint that is telling you, actually, let me go to the formulation 2 straight away. A constraint that is telling you that Yij, the share of the demand that is being satisfied by depot J, it must be, first of all, greater than or equal than 0, and second of all, it must be less than or equal than xj, where xj is either 0 or 1. So it's a fairly immediate inequality that you can write down right away. The constraints yeah, so the other constraints are the satisfaction of the demand constraint of client I, which means that the sum over all depots j of yij of the portion of the demand that is being satisfied must sum up to 1. Otherwise, there is some demand that is not being satisfied. And the objective function will consist of 2 parts. One part is defines corresponds to the transportation cost, that is the actual transportation cost, and the second part corresponds to the cost of opening a depot at a particular location. So eventually you would arrive to a formulation of this type, where you have a minimization of an objective subject to a constraint, and then a system of constraints that are logical, something that is a physical constraint, something that is basically a continuity of flow constraint, and then another constraint that is a logical constraint to enforce the definition of the variables. and some non-negativity, and also some constraints that are like enforcing like some variables to be binary or integer. So this is an example of a formulation problem. I just realized that I should probably give you guys like a list of types of problems that are going to be on the exam. So regarding that, there definitely would be a formulation, at least one formulation problem. There are definitely gonna be a formulation, like a problem that is regarding the exact kind of the exactness of solution of a simple problem. So it's either gonna be a problem regarding like a problem regarding dynamic programming problem, or it's going to be a problem about total unimodularity, or it's going to be like a problem that is to show that the solution is like the solution that you are getting out of a heuristic is exact. And then there will be a problem on duality, like some problem that is covering duality. So these are the three types of problems that are gonna be definitely included in on the exam. I know that it's quite broad at this point, but it's at least now you can go back to the homeworks and see in which direction it might be going, because I will be putting together the formulation of the exam problems are going to be simple and relatively similar to the ones that were given for the homework. I think there will be 4 problems. So the 3 of them I have named essentially the general idea of what they're gonna be. The 4th problem is like could be like something similar from the same kind of direction of of one of these 3 topics, or it also could be another topic as well that is covered. Anyway, you will be able to have to take one of the problems back home and resubmit it. I think our exam is on Friday, and you will be able to resubmit it after a weekend. So one problem that you are having difficulty with, you will be able to deal with at home, just to make sure that your stress is kind of mitigated this way. So don't worry, like if you don't solve everything on the exam, you still will have something, some time to think about it on your own. Obviously, no no cheating when you are doing it at home. No, like the policies are still strict. It's just for you to have a little bit more time about thinking on the problems. Actually, just one problem that you couldn't quite get through during the exam itself. Any other questions? Can I help you with anything else? I can actually go over the formulations, the rest of the formulations that were given for the homework, or I can try to cover at least one of them. What was the homework formulations? Let me try to see it. Is there a particular problem you guys want me to go over from the first homework set, for example? I think the 195 was a challenging one. Oh, with the tennis problem. Okay. Yeah, that's a good point, by the way. So the tennis problem, I can also go over the solution to that. That was a challenging problem too. So it was kind of the extra point, the extra point problem, and it's from the third homework set, right? So it's already been submitted, right? So we have n players, n courts, and n rounds. And we are trying to set up a court, like set up the scheduling so that no one is playing is in the same couple, in the same kind of subset of people. Okay, so the person who asked the question actually just dropped out. Is that correct, guys? Do you want to hear more about the tennis problem at all?
Actually, I'm asking the question.
Oh, you asked the question? Okay.
Yeah.
Oh, okay. Okay, that's right. Okay, so it's right. So let me pull up the actual solution to that. Tennis problem. Okay. Let me share the screen. Right. So basically, we are like, we start by defining the variables as always. We are having the variable. Let me actually increase the. So we are defining the variables. The first thing is that the variable is going to be x, I, j, k, l, t. So it's gonna have 5 indices. It's going to be equal to 1 if I, j are playing against k, l at period t. So this is a binary variable. X is a binary variable, and it has 5 indices. I, j, k, l are from 1 to x, to the number of players. T is from 1 to z, the number of periods. The constraints are saying that, well, first of all, we need to make sure that there is symmetry, right? That x I j k l is equal to x j I k l, and also x I j k l is equal to x k l I j. So it's the first thing. And also we need to make sure that basically no like if I is equal to j, or k is equal to j is equal to k, or anything, then x I j k l is equal to 0. So like it holds for any t. That's why I'm not putting any t in here. Then we need to say that the number of quarts is limited by y. So for every t, we are having the summation over ijkl such that I is less than j, I is less than k, k is less than l, and l is not equal to k, then xijkl is less than or equal than y. The summation over xijkl is equal to y. Essentially, we're saying that the summation of all of the subset of players that are playing simultaneously, the summation of such of x's is going to be less than or equal than y, because we just cannot fit more, like the number of ones that corresponds to the same t must be less than or equal than y. Is everything clear that out of what I'm talking about right now? Are there any questions so far? Yes, meaning that everything is clear. It's clear. Cool. So now we are summing over TKL such that so we just need to make sure that a pair IJ is never the same. So so neither IJ nor KL is never being repeated in the same way. So the sum over TKL such that K is less than L is less than or equal than 1 for every IJ. So it doesn't matter. So like summation over all t. So for that, like if we sum over, if we consider all of the t and all of the opponents KL, the xij like must be equal to 1 only once, out of all of the sets of indices that we are considering. Therefore, the summation must be less than or equal than 1. It could be equal to 0 if ij never played together, but it cannot be less than like greater than 1. The objective that I actually I first formulated as minimization over x, maximization over I, summation over t of 1 minus maximum over klj of xijklt, which is, so here we are having the maximum number of times that a person is like the maximum number of times that a person is playing. Like it's okay, a maximum number of times that like a pair is being okay. So we are like here we are basically considering I, specific I. So for a player I, this is the maximum number of times that a person is playing. 1 minus this maximum time is essentially the number, essentially it corresponds to a time when like when they do not play. So we are talking about the number of times that they do not play, and then we are making a summation over t, meaning that we are summing up all of the times that the player I did not play, and then we are maximizing over I, which corresponds to the case when a person did not like we are maximizing over the players the number of times that a player did not play. So we are finding a player like this part of the problem refers to finding a player that has did not play for the most amount of times, and then we are minimizing this maximal amount of times that a person did not play by adding a minimization over x. So we are eventually we are minimizing over x, and then we can simplify it because the summation over t, since it's from 1 to z, we can replace this with this, and then we have minimization of maximization of negation So it's going to be a maximization of minimization of a plus sign, and then we can essentially reformulate this maximization of minimization and then the summation in this form by introducing a new variable zit that is greater than or equal than xij and less than or equal than sum over xij k l and t. And eventually we can reformulate it as maximum like just maximum over y of over variables z x y. Like we will add another variable y that is less than or equal than summation over t of zit for all I. So it's also like a vector variable, and y and is real, and z and x are binary variables. So it's like everything like the logical line is being basically ended here when we have constructed the objective. It's quite like weird and non-trivial how you construct this objective, but eventually you reformulate this objective as a linear objective function. You can see, like, I will share this file with you if you want, and you can see exactly how to put this into code, and you can reason yourself. You can think about it more, why exactly this code must work, and what exactly are the meanings of the variables y and the variable z that were introduced in order to simplify this objective. I can talk more about this. I know if you have time for an office hour, we can agree and meet separately for an office hour. Meanwhile, I think that's it. That's all I wanted to cover. So I'll see you next Friday for the exam. And next Thursday for the exam, and this Friday the discussion is canceled, and basically you can send me an email if you have any questions. We can agree to meet, like agree for an office hour. It's Thursday. Yeah, it's Thursday. Thank you.
So, Professor, your office hour is tomorrow, right?
My office hour. So I have decided, since there was not too many people who were coming with the questions, I decided that I would make it floating office hour,
Oh, okay.
and we can just agree to meet at some point for an office hour. Tomorrow I just cannot do it tomorrow, but sometime next week, like Tuesday, for example. I already have a person who have suggested to meet on Tuesday. If you would like to spend some time, we can meet on Tuesday too.
Okay, I'll email you if I need the.
Sounds good. Sounds
Okay.
good.
Thank you, Professor.
Sure.